Hello, are you able to?
Yes, sir.
Yeah, we can start now. I hope you are able to see the screen also, right?
Yes, sir.
Yeah. So today, what we are going to discuss is all about how the dimensionality reduction techniques are used, the mathematics behind dimensionality reduction techniques for health and intelligent systems. That is what we are going to discuss, right? So first of all, what is dimensionality reduction? Mathematically, how you define that problem, right? See, the data, right? So the medical data, right? Whatever we collect through the sensors, right? So that is represented here as the random vector u, this one, right? Which is actually in the higher dimension. It could be like EEG signal, ECG signal, right? And it could be like MRI image, right? So which is basically having, right, the vector size is really large, right? So for example, very small 50 cross 50 image size, right? So that itself is having 2500 values, right? So you can imagine how much bigger it is, right? So it's actually the vector size is really large here. So we have here the vector u, which is in the higher dimension space, m cross 1, we need to project to the lower dimension space, right? So which is of n cross 1. So that is the problem statement here, right? So there is a need for the matrix A, right? So here the vector u. Any problem? Is it okay? Able to hear?
No problem, sir. Please continue.
Yeah. So this vector, which is say m cross 1 here, we need a matrix A, which is of size n cross m, so that we can get that reduced dimension, which is of n cross 1. For example, as I told you earlier, that image, right? So your typical value could be something like m equal to 2500 cross 1. I mean, m is 2500 and this vector size is 2500 cross 1, right? So you have the data, the raw data collected to the sensors, right? So it is like U1, U2, and so on up to this U2500 elements are there, right? You need a matrix A such that this is getting converted to V1, V2, and so on up to this V13. So this is going to have the size of 13 cross 1, and this matrix size is of dimension like 13 cross 2500, and this vector is of size 2500 cross 1, right? So I mean, this 13 I have given as an arbitrary number. It could be something else also, right? So this 13 I just like that I have chosen for one particular set of data, right? So what we are achieving here, right? So we are achieving representing that data with less number of elements, right? So originally we had 2500 elements, but that is now represented with 13 elements. We are able to store them, right? So more efficiently, and we can use them for classification or whatever the model you develop in ML algorithm, right? So like regression also. So we can actually make use of this dimension reduction technique as the first stage to do it. But is it really possible to achieve this much reduction, and why this is possible? To understand this, I just wanted to give you some illustration with 2D and then come back to this original slide to understand the concept of the dimensionality reduction technique, right? So we go for one simple example, then we'll go for that original track to understand about that, right? So say, for example, you have a data. So let me Okay, so let me take like okay, let me take this. Okay, fine. Okay, I have it here. Right. So you consider this. This is the 2D data what we are having here, right? So this is a 2D data, right? We have here X and then Y, and these are all the data points, right? So here you can see that these are all the data points what we are having, correct? So this one is to demonstrate for 2D to 1D. Then actually we can think of mapping from 2500 to 13 dimension. The same procedure we can follow to achieve this, right? So first we will understand about how this is achieved for 2D to 1D, right? So this is the 2-dimensional data what you are having here. So as you can see that this is the data which we can think like collected through sensors, right? So it is like this. Okay, so now any point, right? The data you consider, right? So that is represented with the coordinate axis, like it is like, x1 comma y1. What does it mean? It is basically the distance from the origin. So that is giving you x1 here, and then this distance. So I request all the participants to mute.
So please continue, sir. Unmute and continue, sir. Gopi, sir, please unmute and continue, sir.
Yeah. Yes.
Thank you.
So
Sir.
now what you see here is this point x1 comma y1, right? So that we are actually representing as the linear combination of the standard basis. Let me take say a different point here. Okay, this point x1 comma y1. So this is actually, we have here the standard basis as 1 0. Okay, so this is a standard basis 1 0, and then we have here 0 1. What does it mean? It means that you are representing the vector x1 y1 as the linear combination of the two vector 1 0 and then y1 into 0 1. And this is the coefficient x1 and y1. This is the coefficient you are getting. I hope this is clear, right? x1 into 1 0 is actually x1 0 and then 0 y1, and if you add you get x1 y1. So self-explanatory, right? Like this. So now what we are going to do now is we are going to find out a new basis. Instead of using that standard basis what we had 1 0 and 0 1, we are going for a new sets of basis now. This is a new basis vector here. So let us consider this the two new basis which is identified now. So let us call this basis as E1 and this is E2 here, right? So it means that the same vector, right? So for example, if I consider some arbitrary vector here, this one, if I am representing using that standard basis, what we did was projected that vector on this x and y axis like this, right? So it is like this. We projected like this, and then we found the distance measured from the origin. So that is why, for example, this is say x2 comma y2. So we are measuring this one as x2 here, and this one we are measuring that it is a y2. The same job I am going to do now, but I'm going to project on a new basis vector. Like this is the projection now. I am projecting on E1 now. Instead of the standard basis, I am projecting it on E1, right? So as you can see that, this is the projection. And then I am going to project that point on E2 as well. So this is the projection, perpendicular projection I'm going to have. So that I can measure, right? So I can measure the distance from that origin to know about that coordinate. This is the distance here, and this is the distance here. So what do you mean by that? This is basically what I am telling here is, say, for example, this distance, what I measured here, let us say that it is P1, and this distance, right? So you projected this point on this E2 and you measured that, that is, let us say that it is Q1. Then we are representing the same vector x1, y1 as the linear combination of P1, E1 plus what? We have here Q1 into E2 vector, right? Earlier, we represented that vector as a linear combination of the standard basis. This is the standard basis what we are having, right? Now we identify a new basis vector here and we found the coefficients as well, this P1 and Q1, right? So I can do this job for all the points, whatever I'm having. But still, we get the two ways of representing the data, right? X1, Y1. So this one using the standard basis like 1, 0 and 0, 1. And then this is same as that of the vector P1, Q1, but represented using the basis vector E1 and E2. What do you achieve? See, here also the dimension is not yet reduced, right? So here also we have two elements here, here also two elements here. So not yet, the dimension is not yet reduced here, right? So what really makes the dimension reduce? If I do this projection for all the points, what you achieve, you can see that, right? So what I'm going to do now is I'm going to project all the points, right? So whatever the points I'm having, right? So all the points I'm going to project, like, in fact, I need to do it for all the points here, right? So like this. And similarly, I need to do this projection of all the points on this y-axis like this, right? So I can do the projection of all the points on the y-axis here, right? So that this is called the standard basis I'm talking about, right? So like this. So now, after doing all this projection, we can actually find out the range. Range means the minimum projected value and then maximum projected value. We need to find out the difference, right? So as you can see here, this is the maximum, right? What is getting projected on this 1, 0, right? So on 1, 0, this is the maximum it's getting projected, and here we have the projection, the minimum is here, right? So this happens to be the range. This is the range here. This is the range of values of this, the points projected on the x-axis. Similarly, if I project it on that y-axis, I can actually find out the range, right? So this is the minimal projection value, and this happens to be the maximum, right? So this happens to be the maximum here, and then we get a range here. This is the range what we get here, right? So this is a range for x, and then this is for the range for y we get here. This range of x and range of y is large actually, right? But when I do this projection, right? So I'll remove those things now. So now you understood what is the projection. So after doing this projection, we got that range of the projection on 1, 0 basis, and then range for 0, 1 basis. I hope you got it right. So this is the range on that 1, 0 basis, and this is the point, right? So you have a range here for the 0, 1 basis. The same thing now I am going to do it for projecting the points on E1 and E2, right? So if I do that, what you get, you see that these are all the projections. These are all the projections what I am doing now. On instead of projecting on 10 and 01, now I am going to do the projections on E1 and E2. What do you achieve? You can see that, right? So this is that projections on E1. If I do the projections on E1, these are all the points on this E1 axis. So this is the range what we get for E1. The same thing, if I project it on E2 like this, so these are all the projections on E2. If I do these projections on E2, okay, like this, of course, this is the here we are having here, and this is the projection slot, right? So like this, right? So if I see the projections on this E2, so we have here the range is available. So this is the range where on the basis vector 1, 0, basis vector 0, 1, and then we are finding the range on the basis vector E1 and then the basis vector E2, right? You understood? And you know that the coefficient is actually determined by the projection point on the corresponding basis, right? So this is giving you the x coordinate, this is giving you the y coordinate, this is giving you the p, and this is giving you the q. As you can see that this is p and q, this is x and y, is like this, okay? Now what you see here, what you observe here, the range of E2, the range of E2 is much, much smaller. This is greater, this is higher, right? This is also higher, but this is very, very less. In fact, if the data is right, even distributed in such a way that this projection is ends up with almost zero also. This range, whatever I'm mentioning here, this range, this will be approximated like zero, like because this range value, say for example, if it is coming like 0.01, it is almost negligible. What does it mean? It means that the Q values are going to be almost zero. So we don't want to use this eigenvector E2. The vector x1 comma y1 is simply represented as the scalar times only the eigenvector E1. So what we achieved that 2D to 1D projections, right? So this x1, y1 is actually in 2D. It is now mapped to what? P1, which is actually 1D. We achieved the dimensionality reduction here. How we achieved? What we did? We projected the points to the new basis, right? So if I do that, what we are actually achieving here is the projection on the another basis, which is perpendicular to this E1. That range we are making them is almost zero. And that is why we were able to get that mapping from the higher dimension to this lower dimension. In this case, it is the explanation is given only for 2D to 1D, but this is true for 3D to 1D, or even if it can be extended for 2500 dimension to just a 13 dimension, like that it is possible, right? So that is what the key idea behind the dimensionality reduction. Why this is happening? Because the data is having some redundant in that, right? So the redundant means, though we say that it is actually represented in 2D, right? So say we say that the data are in 2D, like what you see it on the screen, right? So it is like 2D, right? So this is the 2D, but it is not really, distributed or scattered in all the regions on the 2D space. We can actually think like the data are aligned in some direction. You can see that, you are able to see that the data are aligned in some direction, right? So suppose that if that direction, if it is identified and the perpendicular to that direction, if it is identified as another basis, because the orthogonal basis only we are considering for getting that coefficient simpler, right? So we have this eigen vector here, E1, this is the basis, and then we have this E2. two basis vector we are actually identifying, right? E1 and E2 here. This is E1 and this is E2. So this direction is actually, it's actually showing the direction of the maximum variance of the data after projecting to that line. So what does it mean? It means that you are projecting the points on this line and you are finding out the variance. You are finding out that variance. That variance happens to be the larger. This variance is going to be the larger. You are actually finding out the direction of the basis vector such that after projection, the variance is the largest. That basis vector is what we call it as this eigenvector. This is called the eigenvector, right? So this is for 2D to 1D. So we found only one eigenvector. Suppose if it is from 2500 dimension, means we have to identify first the direction of the maximum variance, right? The next largest direction of the maximum variance and so on. So those are all the eigenvectors we have to find out, right? So essentially what we did was we computed the eigenvector, okay? Eigenvector for the covariance matrix, and that, right? So that is what we did, and we projected the data using that eigenvectors, right? So strictly speaking, for 2D, we are actually getting two eigenvectors, E1 and E2. Suppose if it is 2500 dimension, you actually get 2500 eigenvalues for the covariance matrix, right? So the covariance matrix size is going to be that 2500 cross 2500, right? In case if the vector size is 2500, and the eigenvalues, right? So if I compute the eigenvalues, you get 2500 eigenvalues. And if I arrange them in decreasing order, like this lambda 1, lambda 2, lambda 3, and so on up to this lambda 2500. And if I plot them, instead of you are arranging them in a decreasing order, and then if I plot those eigenvalues, you can see that the values actually drastically gets reduced after a certain number of the eigenvalues. Say, for example, after 13 values, the eigenvalues are going to be almost 0. This 13, again, it is a arbitrary number. It depends upon the data. It will vary. This 13, I am just putting some arbitrary right here, like. So now what we have to do is, though we have 2500 eigenvalues, we need to identify the eigenvectors corresponding to the significant eigenvalues. It means that you are going to select the largest, say 13, okay? So 13 eigenvalues you are going to select, and then you are going to find out the 13 eigenvectors. Then you need to form a transformation matrix E, in which this we know that we want the transformation matrix which maps 2500 to 13. So this size is 13 cross 2500. Each eigenvector is of size 2500 cross 1. Okay, because we have a covariance matrix of size 2500 cross 2500. So eigenvalues are scalars, and you are finding out these eigenvectors. Each eigenvector is of size 2500 cross 1. And these eigenvectors, you are going to arrange them in a right row wise. The 13 eigenvectors, what we identified corresponding to 13 significant eigenvalues. We have 13 significant eigenvalues, and we are arranging them in a row, right? So these eigenvectors, this forms the transformation matrix. So this eigenvector E, and if I am multiplying this vector, which is actually in the higher dimension, which is 2500 cross 1, which we can convert to the lower dimension, because the size of this E is 13 cross 2500, so that this will give you the 13 cross 1. The dimensionality reduction is achieved. I hope you got the point. So the motivation behind the dimensionality reduction, now I hope you got it, right? I repeat whatever I told in a short form. What we are doing here is we are looking for the data and we are exploiting the redundant, right, in the data. And that is why we are able to get the dimensional reduction, right? So what we did, we have given a data. I think you need to mute actually. Is there any?
Sir, someone is opening. Sir, please, you can unmute and continue, sir.
Right. So now the steps involved is very simple, right? We have two steps in that. The first step is to find out that covariance matrix CX given a data, right? So let me tell you that final summary. If you are given a data, this is the data given, right? It could be, you can imagine whatever the data you are provided with, right? It could be the image, it could be the signal, right? Like that. So you are having a group of data. I want to reduce the dimension, right? So say this vector individually it is of size 2500 cross 1, right? The first step is actually you have to find out the covariance matrix. We need to estimate the covariance matrix, right? So how do you estimate that? It is we have to take like x1. Basically, covariance matrix is expectation of xx transpose minus mu x transpose. This is the covariance matrix basically, but we are now doing estimation for the first term, this part here. For computing this part, we are actually multiplying x1 transpose, x2 transpose. It goes like that. And we have here xn transpose, and you need to take that average. Suppose if I have n data here, I need to divide with n. This is that the first part is over. The second part, mu x, is basically we need to take an average of all the vector x1, x2 goes like that up to this xn and divided by n. This is where mu x. We have to compute this mu x transpose here. So that is the second part here. And we need to subtract them so that you can get the covariance matrix. Okay, so that is the first step. The second step is you have to find out the eigenvalues. It's basically the determinant of Cx minus lambda I that is equal to 0. You get these eigenvalues, and then these eigenvalues you need to arrange them in a decreasing order. Suppose if the size of the vector is 2500 cross 1, the covariance matrix size is also becoming 2500 cross 2500. And your eigenvalues, the number of eigenvalues are also going to be 2500 here. And you are arranging them in a decreasing order. And you are selecting the significant, right? So you select the significant eigenvalues, right? So say for example, you are selecting like 13 eigenvalues, right? So like lambda 1, lambda 2, and so on up to this lambda 13. This is what you are selecting. Significant means other values are almost become 0, right? So, and then for every eigenvalue, significant eigenvalue, you are going to find out the eigenvector, right? So basically, this is nothing but Cx ei, the vector that is equal to lambda I times ei. You need to solve them, right? You need to find out the vector ei that satisfies this equation. Cx ei equal to lambda I ei. Lambda is the corresponding eigenvalue and ei is the eigenvector. So you got now eigenvectors, and then you need to construct a matrix. That is what we are interested on, right? The matrix you have to construct. So whatever the eigenvectors we got, we arrange them in a row wise like this. We have this E13. So this is actually becoming the transformation matrix now, because the transformation matrix size now it is becoming 2500 cross, I'm sorry, 13 cross 2500, right? So this is 13 cross 2500, because each row is of 2500. We have 13 rows, so 13 cross 2500 is there. So that's all. So finally, we are going to do the dimensionality reduction, right? So any vector, right? So we have something like a test vector is coming, or a new vector is coming, new data you are collecting, right? So we simply multiply with this matrix A for getting the dimensionality reduced, right? So this is the vector, which is Y test. This is of size 2500 cross 1, that is now getting reduced to 13, provided the matrix size is of 13 cross 2500. That this is the first part of first method where we can actually achieve the dimensionality reduction technique. This is popularly known as PCA, principal component analysis, right? So this is what we use it for representing the data. But what is the drawback, right? So we'll see what is that drawback of this, right? So yeah. Okay, so this is what I was telling. You have the vector, and this is going to be your eigenvectors, and then you are projecting, right? So after doing this projection on this E1, these are all the projections, right? So these are all the projections you get here, right? So points you will get on this E1, and that is what 2D to 1D is achieved using this. As I told you, this is what we are going to use, this covariance matrix and then eigenvector, and you have to find out the transformation matrix to do it. But what is the problem in this? This is okay, this is popular, but what is the problem? The problem is it doesn't take care of the class label. Suppose if you are doing the dimensionality reduction for classification purpose, right? In most of the applications, right, you may need to detect whether it is cancerous or not, like that. I mean, there are many applications for that, right? So the class is attached to every vector. Here itself, you can see one is blue, another one is red. So the class label is there. But while calculating this scatter matrix, this is the covariance matrix. In pattern recognition terminology, the estimate of that covariance matrix, what we did in the previous discussion, we called it as a scatter matrix. Right, so both are same only. Covariance matrix is statistically we have to do, like expectation operator we have to apply to do that. But scatter matrix is basically we need to use only the estimate of the covariance matrix, right? So whatever we did earlier, right? So that is that scatter matrix here. Okay, so now what is the problem in this? The class label is not used, right? So we have a class label, right? This is all class 2 and these are all class 1. That information is not explored for getting the transformation matrix. There comes you, right? So this one I'll come little later. There comes the linear discriminant analysis, LDA. So there is a spelling mistake here, right? So this is LDA. So whatever we discussed earlier is what we call it as this PCA, principal component analysis. Now this is LDA here, right? So what is it LDA basically? See, the drawback of PCA, whatever we did earlier, doesn't care about the class label. That is the drawback, right? So we are not taking care of the class label to do this projection, right? So now what if I use that, right? So for example, again, if you see it in 2D example, right? So you have a data, 2D data like this, right? But now this time I'm going to have a class label also. So like one is red, right? So the another one, another class we have here blue, right? Like this. So the now in case of PCA, it doesn't care about that class label. It tries to identify the data where it is getting varied, right? The variations are more after doing this projection. That is what we discussed in case of PCA. But now in case of LDA, right? So LDA, what we are going to do here is we are going to find out again new sets of bases, right? So somewhere here, say for example, I'm finding out this basis in such a way that after projection, right? So if I am doing this projection on this basis vector, right? If I do that, okay, if I do that, the vectors should come after projection. I'm telling, after projection, the vector should come close to each other if it belongs to the same class, right? And I do this projection for the blue class also here. So if I do this projection, right? So if I do this projection here, after doing this projection, right? So all these blues, right? So it's getting projected on this line, and this should come as close as possible. That is one thing, one of the condition. The another condition is the mean of this, right? So the mean means the midpoint of this one, this one we need to have a wide apart. This gap I need to make them as large. Here we have two requirements. We have two requirements, right? One is after projection. In both the case, it's after projection only. After projection, vectors should come close to each other if it belongs to the identical class, right? Right. So if it is a red, then red should come close. If it is a blue, then blue should come close. That is one of the requirement. The second requirement is the centroid or mean. The mean vectors for the individual class after projection, after projection, right? That should go, right? What? The distance should be larger here, should go apart, right? So should be far away from each other, right? Away from each other. So it means that distance you wanted to make larger, this distance after projection, right? The mean vector that should come very far. This one you wanted to make larger, but within that class that should come very close. So we need to find out the basis, right? That does this job. So to achieve this, in case of PCA, we had only one covariance matrix. Of course, we did the estimate of the covariance matrix. We call that as a scatter matrix, right? So we had only one scatter matrix in case of PCA. But in case of LDA, we have two scatter matrices. One is between class scatter matrix. The another one is the within class scatter matrix here, right? So here since we know the label of the vector belongs to the class, right? So we are writing like Xij. Xij means it is the ith vector in the jth class, right? So it is like, for example, this one is the first vector in the first class, right? So it is like x11. So this is like what? x21, meaning the second vector in the first class, like that. So that is that. And for example, if I represent this vector, this is the first vector in the second class, and this is the second vector in the second class, and this is going to be your third vector in the second class, like that. So we are representing that vector as with subscript xij here. There it is only xi, but here it is a xij. And the number of class here, it is r, lowercase r. In this example, this r value is 2 because we have only 2 class. So this can be generalized for many classes also, right? So in this case, you need to find out 2 scatter matrix instead of 1 scatter matrix. We need to find out 2 scatter matrix. One is the within class scatter matrix. Within class scatter matrix actually helps in, right, the first objective, right? So we know that the first objective is after projecting the vectors should come close to each other if it belongs to the same identical class, right? So SW is responsible for that. And here we have SB, between class scatter matrix that is responsible for making that mean vectors to go apart, right? So that gets separated, right? So you can see that in case of between class scatter matrix, we are using only the centroid or the mean vector of the individual class, right? In the raw, future dimensional space, meaning in the original dimensional space, we have to find out the mean. See, for example, in 2D, right? So if I have a two class problem, like this is one class, right? And then you have here another class is there, right? So what we are actually finding here is we are finding out the centroid here, mean vector, taking that average, and then we are finding out the mean vector here, taking that average, and this one only we are saying that it is C1, and this one we are saying that it is a C2. Here we have K, right? K and K is ranging from 1 to R. In this example, R is 2. So it is like K equal to 1 or 2. C1 and C2 is this mean here. Okay, then what is C? C is the average of this C1 and C2, right? So that is going to be what? C here, right? So we are finding out the between class scatter matrix here, right? So it is like Ck minus C, the whole transpose, Ck minus C, right? And this Nk is the number of vectors in the kth class. So sometimes in the training data, the number of vectors in each class need not be what? The same. Say, for example, in class 1, you may have 100 vectors, and class 2, you may have, right, say 75 vectors or 50 vectors, like that, right? So this is going to be our 100, and say this is going to have 50 vectors are available. So in that case, your N1 is 100, and then N2 is 50 here. So Nk is the number of vectors in each class. Ck is the mean vector computed for the kth class. Like C1 is the mean vector computed for the class 1, and C2 is the mean vector calculated for the class 2. So this is the way how we computed SB. And what is SW? SW is we are simply adding the scatter matrix computed for the individual class. As you can see here, this is the scatter matrix computed for the jth class, and then you are repeating this one for j equal to 1 to R, right? So you know all the terms I already explained. Xij means ith vector in the jth class, Cj is the mean vector of the jth class, Xij minus Cj the whole transpose, and Xij minus Cj, and like this. Once we compute this SB and SW, of course, what is the size of SB and SW? It depends upon the size of this vector, right? So let us say this vector is in the higher dimension space. Let us say this vector is of size 2500 cross 1. Then this between class scatter matrix is going to have the size 2500 cross 2500. And SW is also going to have the size 2500 cross 2500. In case of PCA, we found the eigen vectors and eigen values, right, for the scatter matrix S. In case of LDA, what we have to do is we have to do this one for SW inverse SB, right? So the steps is actually after computing this SB and SW, we need to find out the eigenvalues, okay? Eigenvalues for SW inverse SB. And other procedure are exactly the same. Once this eigenvalues are computed, you have to arrange them in decreasing order, lambda 1, lambda 2, and so on up to this lambda 2500. And then you need to select, right? So you need to select the significant eigen values, right? So let us say that you have selected something like 13, lambda 1, lambda 2, and so on up to this lambda 13. This is a selected one. And then you need to find out this
ఎక్కడ
eigenvector here, right? You need to find out the. Hello. Okay, right. So now you have to find out the eigenvectors for the individual eigenvalues like E1, E2, and so on up to C13. And then as usual, you need to construct that matrix A with all the eigenvectors are arranged in the row wise, means corresponding to the significant eigenvalues. You have to arrange them in a row wise so that this dimension is going to be like 13 cross 2500. Then you can project it. Once you start projecting, right? So it's now the projection is like y equal to ax, right? So x is 2500 cross 1 as usual, right? This is going to be your 13 cross 2500, and then you get a projected data. So, but this projection data differs from the projection data what we got it from that PCA. Here we can actually get the vectors to come close to each other if it belongs to the same class. That is what we achieved here, right? So this is about that LDA, right? So this is what I was telling. We need to find out SW inverse SB, okay, and find out the significant eigenvalues and the corresponding eigenvectors for doing this projection, right? So now this is the one application done using this PCA and LDA projections, right? And for the real data, of course, this is right for the visualization purpose only. Here we have here this matrix is what we call it as the distance matrix, right? Distance matrix represented in a visual form. Why the distance matrix representation is needed? Basically, if the dimension of the vector is 2D or 3D, we can visualize, right? We can see to the data through our naked eye, and we can actually see to the right the plot, and we can see how the data are looking. But when you have a data is of size, say for example, even with 13 cross 1, if I have a data like x1, x2, and so on up to say for example x350, right? So there are 350 data available, okay, and we don't know how it is looking, right? Because the vector size is very large, like 13 cross 1, let us say 13 cross 1. After doing this dimensional reduction, each vector is of size 13 cross 1, right? So now we don't know how the vectors are arranged in that space, right? For that, what we do here is we find the distance. You take x1 and find out the distance with x2. First, we'll start with x1 itself, okay? So x1, then we take x1 with x2, and then x1 with x350, done. Then we take x2 and we see how it is distance with x1, x2 with x2, x2 with x3, and so on up to this x2 with x350, done again, right? So like that, we can repeat. We can go for x350 with vector x1. These are all the distance we are actually finding out. 650, then x2. It goes like that. And finally, x350, right? Right? Then you understood, I hope you got it, right? So we are keeping the first vector fixed, and we are finding out the distance with all the vectors here. Similarly, we are fixing that second vector fixed, and we are finding out the distance with all the vectors. Similarly, the 350 vector also we are doing that. So how many we are actually finding out this distance, right? So this one we are arranging them in a matrix form, right? So that matrix is called the distance matrix here, right? So this is the distance matrix what you can see after doing this projection. In this example, you can see that. So this is the first vector, and this is the first vector, and this is the distance. and the distance is looking black, it means that they are very close. The first vector and first vector is very close, so it is looking black. First vector with second vector is also very close, it is looking black. So you can see that up to 35 they are looking, they are almost having black. It means that those vectors are very close. The 35 vectors after projection, right? 1 to 35 vectors after projection, they are close to each other. That is what it is showing. And when I see this bright region here, like 0.9, 0.1, so they are not very close, meaning these 35 vectors, the 1 to 35 vectors are close, and this 1 to 35 vectors, right? So say this is 1 to 35, and this is 36 to, right, 70, right? So these are all the different vectors collected, right? So like 71, right, to 35, right? So like you have here 106, right? So you are actually having 35 vectors collected here, right? So goes it in that way. What we really found was the first vector with first vector with second vector, first vector with third vector, and so on up to this 35. And this vector with this vector we found. Whenever I am computing the distance within this class, they are very close. That's why it is showing black. And similarly, 36 with 36, 36 with 37, 36 with 38, and whatever the vector is available between this 36 and 70, if I find the distance value, they are also close. You can see that. But if I take one vector from here and the another vector from here, that is the first vector from here, and 36th vector from here. So that is that the first vector from here and the 36th vector from here. I hope you are getting that, right? So that is bright now. So this is that first vector, and this is the 36th vector. First vector and 36th vector, we are finding out the distance that is looking very high. This is 0.9, something like that. So what it really means, it means that whenever I see here the brighter region means it is far away, and this dark, the black, means it is close, right? So as you can see that this is the another class, they are closer. This is not looking good. This is somewhat okay. This is good. This is not looking good. This is also not looking good. This is fine. So actually, we ideally speaking, what we expect here is all these values are supposed to be very large, 1. And the block diagonal, we can say, we need to have that one as pure black. That is the ideal. That is the ideal thing, what actually we expect after projection. If you want that accuracy to be very high, the data needs to be projected in such a way that after projection, we need to have a proper block diagonal matrix, meaning this diagonal values are all going to be 0, and these values are going to be higher value, like maximum 1, right? So that is what it shows, right? So normalized 1, so you are getting this maximum, this region. See, this is the one done using PCA, and this is the one, the same job only, the same distance matrix, projected using PCA. This is projected using LDA. You can see that LDA is doing far better compared to your PCA, because this and all the places where we don't like to have zeros. This needs to be the brighter actually. We wanted the diagonal, anyhow we have dark, that is fine, that is coming, but still there are other places where we are getting this dark, right? So that is not acceptable. What it really means here is the second class and the fourth class, they are very close. So if I am giving the input from the second class, there is a chance that it may say that it belongs to that fourth class. Error will come into exist, right? So in the classification, the performance of the projected data using PCA is actually doing not good. But it is not always true that LDA performs better than PCA. It is not like that. If I want to compare LDA versus PCA, we cannot claim that always LDA is better than PCA. If you have more number of data, sufficient number of data, definitely there is no doubt LDA will do better, right? But if I have limited data, because of the limited availability of the data, sometimes PCA may give you a better, right, classification compared to that LDA projections. We cannot always declare that LDA is doing the job better. There is one paper on PCA on versus LDA, right? So you can actually look for that paper. I'm not going in details about that, right? So there are situations, I mean, this is actually published in IEEE transactions on pattern analysis and machine intelligence, where you can see that it is not always we can claim that LDA is better than PCA. There are cases where PCA can also do better, depends upon the number of data what you are having, right? So now we are moving to another technique called KLDA. This is the most important and slightly complicated, but we'll discuss this one in detail, that KLDA, right? So what is that about? Now we understood what is that projection, right? So projection means we need to find out the direction where we can project the data. After projection, right, we achieve the requirement. For example, in case of PCA, we achieve the requirement that after projection, the variance should be maximized. That is the goal in case of PCA. But in case of LDA, we had two goals. After projection, the vectors within the class to come close to each other, and the mean of the various class, right? The mean vector of distinct or the different class, right? So distinct class needs to be, right, apart. So this is the two goal in case of LDA, and we know how to do that. This is having only one scatter matrix, right? Yes, but this is going to have two. One is SW, another one is SB. So you know how to do the procedure, right? I mean, we find the scatter matrix and find out the eigenvalues, select the significant eigenvalues, and then corresponding eigenvectors, and then we can construct the transformation matrix, and then we can do the projection. The same thing here also in case of LDA, but only difference is we have to use SW inverse SB. Instead of using a single scatter matrix, we have to use this one for doing that, finding out the eigenvalues and, right, the eigenvectors corresponding to the significant eigenvalues. So, okay, fine. Okay, fine. If the problem looks simpler, right? So, but there are cases, right, where you are even after applying this LDA, right, we will not get the vectors well separated, because the same example I can say you here. So this is the 2D data again, right? So we'll have a example for 2D data, and then we'll have a generalized explanation, 2D data. So in case of 2D data, this is one class, right? So we have here, this is one class. The another class is here. This is the another class. You see that? I mean, the blue circles are surrounding the red circles, right? So in reality, the data are looking like this only. Okay, so whatever the direction we find, right? So this is the two basis vector you are having, right? So suppose that if I am identifying one basis vector like this, right? So let us take a different color, right? So you are finding out that basis vector of this, right? So now you are doing this projection of this red, here, right? So this is the projection. So you get all circles here, right? So now you are going to do the projection of blues. If I do this projection on blues, these are all the projection on blues, right? You see that you are getting the data overlap. This is the blue. Say this projection overall is fine. Here, when I do this projection, this is fine here, right? So this region, and all is fine. But there are regions here which is getting overlapped in this, right? So this is the overlapping, right? So wherever you find in this example, whatever the direction you find, right? So in 2D, right? So green color, right? So the vector, what I consider, you can imagine any other basis you consider in this 2D space, wherever you draw, if I project, you will get overlapping, right? And hence you can't achieve the goal of this LDA. This LDA goal we cannot actually achieve. It is not possible. So what we do here is that we are actually applying some trick. So the trick is we are mapping this one to the higher dimension. This is actually in 2D space. We are, instead of doing dimensionality reduction, we are mapping this one to the higher space. Say, for example, 3D space. And then you come back to this 1D space. Project back again to 1D space. What is that? What I'm telling here is, here you can imagine these blue circles and red circles on the board. So this is the screen what you're having. This is on the screen or board, whatever you call it is, right? So it is like that. Now what I'm telling here is, you imagine the mathematical technique that project the red vector to come out. Like, so let us say this is on this board, right? So you have here, this is a 2D, right? It's on the plane. So I have plotted on the board here, right? So, and this blues are all is surrounding them. Now what I'm saying here is, you project to the 3D space such that only the red is coming out. If I project outside the board, the reds and all is coming out of this plane. Only blues are there. Then in the 3D space, this is 2D space, right? So you are actually, originally it is 2D. Now when I projected to the outside this board, now it becomes 3D. Now I am considering one line, which is actually 1D. I'm considering 1D on this, right, space, and then I am projecting this, because you see that all the blues are there on the board only. All the blues are there on the board. So if I project the blues, you get here, every blues are available here, and the reds already you took it out and it is there in this space, right? So if I project those red here in this, right, on this 1D space, all reds will be here. Now you can see that there is a good separation between this blue and red, right? So instead of going for finding out the eigenvector in 2D space, which actually after projection ends up with what? Overlapping. We do the trick of mapping the vector to the higher dimension and then bring back to the lower dimension. This is the motivation behind the kernel LDA, right? So I hope this is clear to you. Now how that is done? In fact, we are going to realize this one without explicit function to map the vector to higher dimension space. What do you mean by that? Actually, I told that you need to map to the higher dimension. From 2D to 3D, you need to map, and then you need to project back to this very lower dimension, I mean 1D like this, right? But there is something like kernel trick. We are going to use that kernel trick. It means we are actually not going to use any function to map the vectors to the higher dimension. That job we are not going to do explicitly, but we do as if it is done in the higher dimension, right? So first, I would like to give you the solution for just like how we did for PCA and LDA. For KLDA, what are the steps involved in getting the basis for the dimension reduction? That I will discuss first, and then we'll see the outline of how that is happening, right? First, I give only the procedure without, right, complete proof, right? So I am giving only the procedure, right? So this is very, very interesting and very powerful. Those who are interested, those who are doing research in, right, classification, all those things where we can reduce the dimension, right? And before giving us an input to any machine learning algorithm, even for a regression problem or classification problem. This is, of course, we can have a classification part here. So the dimension reduction technique using KLDA, right? So using KLDA, right? So what are the steps involved, right? First of all, I'm going to give you the explanation with only three class, and each class is having some few vectors like x1, 2, say 3 vectors are there in the class 1. This is for the explanation purpose, but this is true for any number of vectors in each class, right? So say for example, x2, 2, so 2, 3, 2, 4. So this is 4 vectors in class 2, and then x3, 1, x3, 2, x3, 3. Okay, so maybe x3, 4, x3, 5. This is class 3. Okay, so you have the 3 vectors.
Sir, voice is not audible, sir.
Are you able to hear now?
No, okay, sir.
Okay, right, right. So now you have 12 vectors, right? So 3 vectors in class 1, 4 vectors in class 2, and 5 vectors in class 3. And I am renaming it as like x1, x2, x3, x4, x5, x6, x7, and so on up to the x12, right? The first step is actually you have to find out this G matrix, which involves this kernel function, right? So like take that x1 and then x1 here, taking the first vector here and take all other vectors, right? So like x1, x2, then k of x1, x3, then k of x1, x4. It goes like that, and then we are going to have this x1, x2. This is that kernel values. I will tell you what is that kernel function little later. So this is like that, and then you take that second vector x2, and then you go for the kernel function k of x2 comma x2 here, and then k of x2 comma x3, k of x2 comma x4. It goes like that, and then k of x2 comma x12. I hope you got this point, right? So you are going to construct the matrix like this, right? So it's a big matrix. I mean, for this particular case, it is 12 cross 12 matrix. You are going to construct that 12 cross 12 matrix like this, right? So say, for example, this is done here. And the third column is K of x3 comma x1, right? So K of x3 comma x2 and so on. Here K of x3 comma x12. I hope you got it right. So we are keeping the first vector fixed here, x1 x1 everywhere x1, and the second vector we are changing x1 x2 x3 x4 like that, and we are computing the kernel function. Similarly here we are keeping that first vector fixed x2 everywhere. We are fixing x2, and the second vector we are having a 1 2 3 4 and so on up to this x12 here. And similarly here x3 you are fixing here, and then you are changing x1 x2 and so on up to this x12, right? So you got it. So the last column, let us finish with that last column here. So the last column here is filled up with what? K of x12 here, right? K of x12, and we have to start with again x1. K of x12, x2, it goes like that, and then finally K of x12 comma x12 here. So this matrix is of size 12 cross 12, right? Because we had all possible combinations here, right? So now, once this matrix is obtained, right? So let us represent that matrix like this. Each column, this is the each column here having. This is the first column, right? Second column, third column, fourth column, fifth, 6, 7, 8, 9, 10, 11, and 12. Remember that this is a matrix. I am just writing, I am representing the matrix in a picture form just for continuing my talk for the next step, right? So this is needed. So I am giving that, right? So this is the matrix, basically the same matrix whatever we had the before, right? This is the matrix now, and I am arranging in a pictorial form, right? This is the first column, second column, third column, and so on. Now what you do here is, you know that in originally there are 3 vectors available in class 1, 4 vectors in class 2, and 5 vectors in class 3, right? So accordingly, you are going to group them. This 3 column from this matrix and this matrix are same. Don't get confused, right? So first 3 columns of this matrix, you have to treat them as the one belongs to class 1. Okay, so this one, and then next 4 vectors, right? So these 4 vectors, you have to treat them as the one belongs to class 2, and the remaining 5 vectors, you have to treat them as the one belonging to class 3. I hope you got it right. So now each vector here is of size 12 cross 1. Originally it could be any size, but now it is 12 cross 1 after computing this kernel function. Okay, so what is that kernel function? Before we continue, I just give you the kernel function expression xi comma xj. There are many kernel functions available. We can, one of the popular thing is actually your Gaussian kernel function. Xi comma xj is given as xi minus xj transpose. This is vector here, and then xi minus xj whole divided by s square. This s square is basically the tuning parameter. This is the hyperparameter or tuning parameter. So this is the one which is actually in your control for getting the better performance, like a tuning parameter here, right? So this is that the right kernel function, how it is defined. This is the way how we have to compute and we are calculating this matrix, and then we are treating that first three column as class 1, the next followed 4 columns as class 2, and the next followed 5 columns as class 3. Once you get a new sets of vector, now this is the new sets of vector what you are having, using these column vectors, right? So using this column vectors, we are going to find out that LDA basis. We know how to compute LDA basis, that I'm not going to discuss again. You know the procedure, right? We need to find out the between class scatter matrix, within class scatter matrix, and then we have to find out what? Eigenvectors corresponding to SW inverse SB. We need to find out these eigenvalues, right? Okay, so in this case you get 13, because the vector size is not 13, 12. I'm sorry, the vector size is 12. So it is get your covariance matrix is of size 12 cross 12. So you get 12 eigenvalues. Out of that, you are going to select only few significant eigenvalues, and then you are going to find out the corresponding eigenvectors, right? Say for example, you are selected only 2 eigenvectors, then you are going to have the matrix A. Let me call it as a matrix A. Matrix A is now constructed using this eigenvectors arranged in a row wise. And remember that this eigenvector is of size 2 cross 13. Okay, fine. Now, this is ready now. Your transformation matrix is ready, which is actually 2 cross 13. Is ready. We can actually map the vector to the lower dimension, which is of 2D, right, from the higher dimension. But the original vector, the raw vector, right, this x11, this is the raw vector, the original vector, which is your data, right? So this size is not actually 13 or 12, right? So this is basically like 2500 cross 1. It's a really big here, right? So this is 2500 cross 1. Okay, but we need to map this vector only to the lower dimension. So let us say you have a vector called x test, which you wanted to map to the lower dimension. You wanted to map this one to the lower dimension. Okay, so now this vector is of size 2500 cross 1. Okay, then how do you map this vector to the lower dimension? Using the transformation matrix A. For that, we have 2 steps in that. First, you need to construct the vector in the kernel space. I mean, using that kernel function, you need to get a vector, right? So what is that vector? Like k of x test, just like how we constructed that matrix here, right? So we constructed the matrix. We kept one of the vector fixed and the another vector ranging all the way from x1 to x12, right? Which is basically the training data, right? So like that, here also we are going to do like x test, and then we are going for x1 here, and then k of x test, comma x2. It goes like that, right? So like k of x test, comma, how many vectors are there, right? So we have like 12 total 12 vectors are there here up to this x12. So we are computing like x test comma x1, x test comma x2, and so on up to this x test comma x12 here. Okay, so this size, in fact, I made one mistake here. Actually, this size is 2 cross 12 only, not 13. Since the vector is of size 12 cross 1, the eigenvector is also of size 1 cross 12. I mean 12 cross 1 by taking transpose. This is going to be 1 cross 12. So this row is also 1 cross 12. So it is 2 cross 12 here, right? So now, once we get this transformation matrix A, and we got this vector, say the vector as K here. We do the projection like the Y is equal to A times K here. K test, we can say like K test. K test corresponding to this X test. We got this K test and then we do the projection. This is 12 cross 1 and this is 2 cross 12. So we got this projection to 2 cross 1. You understood, right? So by doing this, what we really achieve here is we are mapping the vector to the higher dimension and then bringing back to the lower dimension. So whatever I told now is the procedure without proof is the procedure what we are having, right? So the dimension reduction technique using KLDA, this is very powerful tool, right? So those who are interested can actually adopt this for their application, right? So for dimension reduction, I repeat. So if you are given 3 class data, each class is having different length of vectors. Like class 1 is having 3 vectors, class 2 is having 4 vectors, and class 3 is having 5 vectors like this. Then you have to construct first the G matrix. G matrix is constructed using that kernel function, and the kernel function is this one. I mean, we can use other kernel function also, but this is the popular kernel function. By properly choosing that value of S as the tuning or hyperparameter, we construct this K matrix or G matrix here, like K of x1 comma x1, keeping that first vector fixed x1 and then keep on changing that second vector like x1, x2, x3 and so on up to this x2 here. Similarly, the second column, you are keeping that x2 as fixed and then you are having the change from x1, x2, x3 and so on like that. It goes in that way. So once this matrix is obtained, this is the matrix G now, the same matrix G. Pictorially, I am representing like this, and these are all the column vectors, right? Using these column vectors, we are treating that first 3 columns as the one belongs to class 1. Where comes this 3? 3 comes because we had 3 vectors in class 1, right? So we are actually selecting the first 3 vectors of this matrix as the one belongs to class 1, and followed by 4 belongs to class 2, and remaining 5 belongs to class 3. Then you need to simply find out this LDA basis, right? So for that, we need to find out eigenvalues, arrange them in a descending order, select the significant eigenvalues, and then find out that corresponding eigenvectors and arrange them in a row wise to get the transformation matrix A, which is of size 2 cross 12 here. And then that's it. This is the matrix which is actually useful for projection using KLDA. This is the projection matrix which does the projection from the higher dimension to the lower dimension. But the raw data, whatever you are having, X test, which is of very high dimension, which is 2500 cross 1, which is really big. What we have to do is, the procedure is, we need to find out K test from X test by applying the same kernel function here with the same tuning parameter, hyperparameter, and apply it to all the vectors, whatever is there in the training data. Remember that for KLDA, for constructing this K vector, you need the training data. So training data also needs to be stored while doing this projection. For even for the testing data, if we want to do projection, your training data is needed. This needs to be stored in your memory so that I can apply this K here, kernel function for the individual training data, so that the size is actually becoming 12 cross 1. You multiply with that matrix A, which is of size 2 cross 12, so that it gets projected to 2 cross 1 here. I hope this is clear for everyone, right? So now we'll see how this trick is happening. Now I told only the procedure, right? Why this procedure is doing that job of mapping the vector to the higher dimension. To understand that, we can actually look for these slides. The kernel trick in KLDA. What does it mean? It means that we are not mapping the vector u to the higher dimension space, right? So you see that we have a vector u, which we need to map to the higher dimensional space using that function called phi of u. But we are not doing this one explicitly. We are not doing this one explicitly, right? We are not having this function at all, this phi. Instead, we are defining what is called the kernel function, which is basically the inner product. Say, for example, if I have two vectors, right? So from the u2 to higher dimension, which is phi of u2 here, and I am finding out the inner product computation in the higher dimension space, which is phi of u1 transpose phi of u2. What does it mean? It means that I am doing the inner product in the higher dimension. This is the inner product in the higher dimension, right? This inner product, right, phi of u1 transpose into phi of u2. This only we are defining it as a kernel function as k of u1 comma u2. Essentially, the moment when I am using that kernel function, as you know, we are using one of the kernel function as the Gaussian kernel function, e power minus u1 minus u2, the transpose u1 minus u2, divided by the tuning parameter or the hyperparameter known as that s squared here, right? So this is a kernel function. We are actually doing the inner product in the higher dimension space, right? Using that, the kernel function. This is called the kernel trick. We don't want explicitly the function phi, but we need only the k, which makes us to work the data in the higher dimension space without explicitly mapping to the higher dimension space. In short, what I'm trying to say here is we don't want phi. We don't want phi. We want only k, but still it works out in the higher dimension space. So how that is possible? That is, say, this is the kernel trick, right? Which is actually used in many places. Like, if you know machine learning, right? So you might be knowing like it is used in support vector machine also, right? So there are many places. Even in regression, we use that kernel, right? Based regression, right? So wherever the inner product in the higher dimension space is needed, I can replace that one with the kernel function, which helps me to work in the higher dimension space without really explicitly mapping to the higher dimension space. So that is what we call it as the kernel trick. So how that is achieved? You can see that now. Carefully, you have to see it's slightly complicated, but you can easily understand if you go through that every steps here. So what is our goal? Our goal is to map the vector u, which is actually in the feature dimension space or where you are collecting the data, right? Sensor data. So that is the vector u here. You wanted to map to the higher dimension, which is actually the vector v. Suppose if I have a vector ui, which actually you need to map to the higher dimension, what? Vi. That is done using the function called phi of ui. So this is the function which is actually mapping that. Okay. So now you are, say, let me put this as vi here. You should not get confused with this v. You are actually now computing the between class scatter matrix and the within class scatter matrix in that space, higher dimension space. Okay. So as you know, in case of KLDA, we are interested on SW inverse SB vector, right? So E equal to lambda E. This is what LDA basis. This can also be written in this form, SBE equal to lambda times SWE, right? So this can also be written in this form, keeping this SW inverse to the right side so that you get SWE here and SBE here. That's what exactly it is written here. This is nothing but LDA, nothing more than that. This is LDA, LDA in higher dimension space, LDA in higher dimension space. And this V is the eigenvector in the higher dimension space, right? Now, another interesting property we are exploiting here to represent this eigenvector. This V is the eigenvector. Remember that it is eigenvector in the higher dimension space. Okay. So now, suppose that if I have a vector space and you have a vectors in that, right? So these are all the vectors, like the vectors are U1, U2, or in this case it is V. Let me put like V. Right, so these are all the vectors in the higher dimension space, V1, V2, V3, V4, goes like that. And you have the vector like Vn. There are n vectors available in the higher dimension space, right? The claim here is the eigenvector V, right? So here you can see that this eigenvector V, right, which also lies in this space. That is what the thing. When this eigenvector V is also lying in the space spanned by these vectors V1, V2, V3, and so on up to this Vn, we can write the eigenvector V. This is the eigenvector, this is also eigenvector, as the matrix M times some arbitrary vector U. This U is not this U, don't get confused. This is some arbitrary vector U, right? So what I mean by that is the eigenvector V can be represented as the linear combination of the vectors that are in the data set. Say, suppose if I have n vectors available in the data set, right? I can represent this eigenvector as a linear combination of this. This can be written like this, these vectors, right? So v1, v2, and so on up to this vn. So this forms the matrix M here. And you have these coefficients alpha 1, alpha 2, and so on up to this alpha n here. And this alpha 1, alpha 2 is what I'm calling it as U here. This U is this one. Okay. This is the matrix M, and this is U here. This U is not same as that of this U. Don't get confused. Once again, I'm telling. Right. So now we are writing this expression SBV V equal to lambda times SWV V. V is the eigenvector here, and your SBV and then SWV, they are all the between class scatter matrix and within class scatter matrix computed in the higher dimensional space. Now what we are doing here is we are replacing the vector V, which is the eigenvector, with MU. Okay, so that is what we are doing. SBV V equal to lambda times SWV V, right? Now what I'm doing here is I am replacing this vector V with M times some arbitrary vector U. This U is different. Again, I'm telling, okay, this is different. So SBV MU is equal to lambda times SWV. Again, this V vector we are writing like U is some arbitrary vector one. Some arbitrary vector you are having, because this is a coefficient. This is like the coefficients are coming, and that coefficient I'm calling this U vector as far as this slide is considered. Right now, what I'm doing, I am multiplying on both sides M transpose. That's what I'm doing here. this is a scalar, so I can multiply here M transpose in this, right? So this is M transpose SBVM, and this is M transpose SWVM. That's what exactly it is done here. You can see that, right? Now we are going to have some interesting result, right? You can see that. You are considering now the vectors in the higher dimensional space, which is constructed like the inner product matrix, right? So as you know that after mapping to the higher dimension, you are getting this vector v1, v2, and so on up to this vn, right? We are actually arranging these vectors, right, in a matrix form by taking that inner product. As I told you, take that first vector, do the inner product with itself, and take this. I mean, you keep this first vector fixed here. You see that v1, v1, everyone v1 here, and then second one is actually changing from v1, v2, and so on up to this vn here, and so on. What about that second column? The second column is actually you have to take this v2, everywhere v2, and then you have to take v1, right? So v2 transpose v2, then v2 transpose v3. It goes like that, then v2 transpose vn. That is going to be the second column, and this is the nth column here, right? I told that once it is done, you get a matrix, right? So you get a matrix, and if I am arranging this matrix in a pictorial form like this, right? So what you are going to do, the first n1 columns, can be viewed as the one belongs to class 1. And then followed by n2 columns, that one you are going to treat that belongs to class 2, and so on, right? If you have only 3 class, then the remaining thing is going to be class 3, or you can even have class 4, class 5, and so on, right? So now like this. Now is the important fact, what I'm going to tell now. In that previous slide, we had here M transpose SBVM, right? And then this M transpose SWVM. This can be viewed as a new between class scatter matrix and within class scatter matrix, right? So that is obtained, this one, right? So this one, M transpose SBVM, and then M transpose SWM can be viewed as the between class scatter matrix and within class scatter matrix computed using that columns of this matrix, meaning the vectors, whatever we now got, right? This first n1 columns and then n2 columns belonging to this class 2 and so on. These vectors are used for computing the between class scatter matrix and within class scatter matrix. If I compute between class scatter matrix and within class scatter matrix for this, that is identically equal to M transpose SBVM and M transpose SWVM. That is what it says, right? So can be viewed as the between class scatter matrix and within class scatter matrix computed using the columns of the matrix given above. These vectors, right? You are using these vectors for finding out this scatter matrix here, right? So now, of course, this V1 is basically the projected from the feature dimension space to the higher dimension space using that function phi. So if I replace this matrix with phi of U1, phi of U2, and so on for V1, V2, and all, you get here, we are representing like a kernel, right? So that's what I said. The inner product in the higher dimensional space is represented like a kernel function, and that is what we call it as the kernel trick. So this is the kernel, right? Matrix here. Okay. Now, as I already told you, M transpose SBVM, which we already computed, M transpose SWM, which we already computed. What is this? This one I am renaming that as SB5 and SW5. What are those things? Those are all the between class scatter matrix and within class scatter matrix, right? Computed using the vectors after constructing the kernel matrix, right? So you have here that matrix, right? So I'm writing matrix in a pictorial form only. I'm not writing fully, right? So this is the matrix and you have a columns. This is the matrix and you have a column here. You know how to get this. This is basically this matrix I'm talking about. This matrix. Okay, this matrix. Okay, so this matrix you are having now, right? Depends upon the number of class you are going to group them. Like say, suppose that if I have 3 class, depends upon the number of vectors in each class originally present. We have n1 vectors in class 1, then n2 vectors in class 2, n3 vectors in class 3, and so on. Say, for example, 3 class here. Using these vectors, you are actually finding out the between class scatter matrix and then within class scatter matrix. That only I am calling it as SB5, SW5. Meaning you can manually calculate SB5 and SW5 using that matrix what you got. You got the matrix and I can compute SB5 and SW5 just like how we did for in case of LDA, right? LDA we did SB, SW. The same way you are going to find out this SB5 and then SW5, right? So your vector E is now ready. This vector is now ready because this vector we can solve. It is possible. But we need a vector Z, which is actually the eigenvector in the higher dimensional space. This is actually in the higher dimensional space. That is the interesting point. We have E, but we need Z, but we already know that this E and Z are related, right? So using that matrix M, this we already had here. You can see that we already had the expression here, right? So we have written this eigenvector V, right, in terms of M into that arbitrary vector here, right? So that vector is coming into picture here. We are able to write that isn't Z vector, which is actually in the higher dimensional space as M into E. The meaning we actually compute the vector E using this kernel trick. Experimentally, we need to compute only E, but we get the vector in the higher dimensional space Z as M into E, where M is the vector constructed using the vector in the higher dimensional space, right? So it is like M is having the vector in the higher dimensional space. We are calling that after projecting to the higher dimension, the vectors are named as like V1, V2, V3, and so on. This is a matrix, right? So you remember that is there in that first slide, right? So you have here M is V1, V2, V3, and so on. Right, so this is the vector arranged in a column form to get this matrix M, right? And that matrix M multiplied with this E, which actually you computed using this matrix, right? Using this matrix, you computed E. Using this matrix, you computed E. And you get this vector Z just by multiplying M into E. But you may wonder, M needs the vector which is actually in the higher dimension. Okay, so how to attack this problem is very simple. If I want to project some arbitrary vector X, what are the steps? First, you need to project to the higher dimension, which is X to phi of X. And then you need to project using the eigenvector in the higher dimension, which is essentially M into E. So it is ME transpose, you are projecting now, ME transpose into phi of X. So if I take E transpose, M transpose, phi of X, you know that this is going to be your M here. This is multiplied. Now we have this M transpose, phi of X is coming. And E transpose is already known, which is actually computed using this matrix. It is already done. But interestingly, M transpose phi of X, M is also having the vector in the higher dimension. which is like phi of u1, and this is phi of u2, and so on. So if I take m transpose, which is phi of u1 transpose, phi of u2 transpose, it goes like that, and that is multiplied with phi of x. What actually you are getting here is the inner product of these two, and that is why you are getting here. You can see that this is the case, right? So you can see here, this is what I was telling. E transpose, this is becoming the kernel function now. So the projection is now achieved. Okay. So this is that example of KLDA compared to PCA. I already told LDA with PCA, and we have a KLDA also. So what we are doing here is we are realizing this LDA in the higher dimension space without really mapping to the vectors to the higher dimension space using the kernel trick, which is called the KLDA, right? So this is the main reference book you can refer. So, and this is that book written by myself on the pattern recognition and computational intelligence using MATLAB. So those who are interested can look for this book and may recommend for that library also. With this, let me conclude my talk, and if there are any questions, I would like to answer before we wind up. Thank you. Thanks for that opportunity, right? Yeah, so Radha Vallabha, right? Yeah.
Yeah. Madam, any doubt you have, Radha ma'am? You can unmute and ask ma'am if you have a doubt. Any other participants, if you have any query to be clarified by the sir, you can unmute yourself and you can ask.
Maybe at the first sight, you might feel this one is difficult. I don't know. Many of you, if you are already knowing this, is fine. I don't know. I just wanted to know how many of you are aware of PCA, LD, and KLDA, this mathematical part earlier. Can you put some statistics so that I can get some idea? PCA? PCA, I hope many of you may be aware of that, right? PCA, I think.
Gopi sir.
Yeah,
actually, participants are not responding, but PCA is known in our image processing, sir. We are using for image compression to some extent, but whatever you have talked about.
Yeah, so actually we had a PCA, LDA, and then KLDA also we discussed, right? So for the dimensional reduction, and PCA we have given a different flavor. I hope you might have got the perspective of PCA, how exactly that dimensional reduction is happening. Is actually we are looking for a different basis in that space. That point I just wanted to stress. Why I'm telling this one is you can actually look for your own basis also. LDA, KLDA is there, but that's a more standard, right? You can see there are, you can actually look for the nature of the data, and then you can actually construct the basis relevant to that, right? So with the objective created by yourself, right? For example, in our case, in case of LDA, we wanted that vectors to come close to each other after projection if it belongs to the same class, and the mean of the class should come apart if it is belongs to the two different class. That is the goal of LDA, right? And KLDA, the goal is when we project from the feature dimension space, whatever the vector you consider in that space, overlapping of cluster is happening. So we need to map the vectors to the higher dimension space and then bring back to the lower dimension space so that we get a good separation between the classes. After that, if you apply the algorithm like support vector machine or any other algorithm, right? So decision rule or any other machine learning algorithms, if you apply, the accuracy level will go higher, and also we are playing with very small number of elements. So the problem of using deep learning nowadays, we are looking for this lightweight neural networks and all. So where we are expecting that performance to be done with few neurons, training is difficult and performance is not that much good. And if I want to have it in the mobile for performing some machine learning algorithms for detection purpose, classification purpose, memory and all is going to be huge if you use the deep learning. And if I go for the dimensionality reduction technique, and then if you perform any machine learning algorithm, the accuracy will increase, right? So any other questions if you have, I can answer, otherwise we can wind up, no problem.
One more time, I request participants, if you have any query, you can clarify, because it is really rare nowadays, difficult to find such much of in-depth mathematics, actually speaking. As everything is available as in the built-in functions, so we rarely found that much of in-depth. So that is nobody is responding.
No issue. So they can actually recording this video, right? So that they can see if they want, right? They can actually look for this video again if they want, so that they can get some better idea about the content. And then if they want, they can actually contact me through mail also, no problem.
Yes, sir.
Yeah.
Okay, sir. Thank you, Gopi, sir. Within a short time, I have approached you and you have generally accepted by our request, sir. And yesterday, sir, actually being the first day, complete theory, sir. No mathematics were at all mentioned. We have just gone through what are the foundations, theoretically only. But today, you have completely cleared the cut of the participants, sir. Some are asking only theory.
Yeah.
The query yesterday, sir. But you give in depth. Of course, dimensional reduction is, of course, the most sought thing, sir, in advanced neural processing. So you gave everything clearly, sir. Thank you so much to you, sir.
Thank you. Thanks for calling.
I hope I have not troubled you through WhatsApp messages or someone that phone calls. If so, excuse me, sir, if I have troubled you.
No issue, sir. Thank you. Thanks for inviting.
Thank you so much, sir.
Okay, fine.
Bye, sir. Thank you, sir.
Okay.
Participants, I share the feedback link in the WhatsApp group. Those who have joined, they only fill the form. I already mentioned. Thank you all for your kind participation. Thank you all. Now I am ending the session.